This is AP Chemistry, Honolulu High School. Today we'll be looking at the first sections of Chapter 13 dealing with the properties of solutions. Now Chapter 4 from earlier in the year was also related to solutions, so if you take Chapter 13 as an extension of Chapter 4, a large number of questions on the AP test really come from these ideas. Not quite as much as the 10-11 that we looked at, states of matter, but about 9 of 75 questions every year, and almost every single year there's a question in the FRQ that deals with ideas from Chapter 4 and Chapter 9. Now, 13.1 deals with the solution process. When we're talking about solutions, what we're really looking at is homogeneous mixtures of two or more pure substances. The two terms are synonymous with each other. Now, they form when one substance, a solute, disperses uniformly throughout another substance, our solvent. So the solute, which we used to say in science was the substance that got dissolved and the solvent that did the dissolving. The way we really look at it is the solute's always going to be present in the lesser quantity and the solvent is always going to be present in the greater quantity. And this is a little more flexible definition of a solution. Now, solutions can be mixes involving any state. Here you can see a variety of different states of solutions and solvents, and overall what the state of the solution would be. And there are a lot of different examples in everyday life of different types of solutions involving really solid and liquid, liquid and gas, and other types of states. So we can have solutions really involving any different state. Typically in this chapter what we're really looking at is aqueous solutions, so solutions of water. Now, one thing to keep in mind is when you have a gas solution made up of a gas solvent and a gas solute, it's always going to form a uniform mixture, so it's always going to be homogeneous. The rest of the situations, it really depends upon what is actually mixing as to what type of mixture, heterogeneous or homogeneous, we're really going to end up with. Now, how does a solution form? Well, one process is the process known as solvation. As the solution forms, the solvent pulls solute particles apart and surrounds or solvates them. So in taking a look at this diagram, our solute here is sodium chloride. And as the water molecules get closer to the ions, the water molecule, one part is attracted to the positive ion, one part is attracted to the negative ion, would pull off those ions and then in solution surround them. So that's the process of solvation. And this is really one way that a solution can form, is really through an attraction of the particles for each other. If the solvent is water, then this process is known as hydration. And what we get is an aqueous solution. Now, in the absence of a strong solvent to solute attraction, like in the last case, the two are attracted to each other, the particles can actually randomly mix together through the process known as dispersion. So when you have two substances that aren't attracted to each other, they can also form a random mix or a solution of particles. And this is really typical when we have nonpolar solutions. So when you have two nonpolar substances, they're going to randomly spread out, and we end up with a uniform mixture in time. So whenever we have two nonpolar substances, like the gases in this room, the dissolving that would happen as we introduce more gas to this room would really be a case of dispersion, not of what we looked at in the last slide, either hydration or solvation. So this is another process where we can get a solution to form. Now, why do solutions form in the first place? Well, the ability of one substance to form solutions really depends upon two different factors. One, the type of intermolecular attractions involved, and that's what we got done looking at last chapter. And two, the natural tendency of a substance to spread into larger volumes when not restrained. And both of these ideas are really important factors into whether something is going to dissolve spontaneously or not. Now, looking at the role of intermolecular forces, there's three fundamental factors that really we look at when we're talking about attractive forces inside a solution situation. The first would be the breaking of the solvent-to-solvent attraction. The second would be the breaking of the solute-to-solute attraction. And then third, we're actually forming bonds as the solute and the solvent particles attract each other. So these are the fundamental intermolecular forces that are at work during the process of solvation. And really what happens is, if this is comparable to really the total of the forces involved in one or two, then a solution is often going to form. Now, what's really happening when we look at these three processes? Well, the first process was breaking the solvent to solvent force. So what type of substance is our solvent? Is it water, hydrogen bonding? Would it be a polar substance? That is dipole-dipole attraction, or is it actually a nonpolar substance, something like carbon tetrachloride? So one of the things we have to do is first break apart the old bonding that existed between our solvent particles. And one thing to keep in mind from what we talked about in the previous chapters, these two polar situations are going to be stronger than the nonpolar situation at the bottom here. And remember, if number 3 was comparable in overall force or energy to really 1 and 2, then solvation would end up occurring. So the strengths of these types of attractions is very important into whether dissolving actually occurs. Now the second thing you have to do is we also have to break apart the solute particles, and that really depends upon what type of solute we have. Is it something like sodium chloride, which would be an ionic situation? That's a relatively strong force that we're dealing with there. Another strong force that we talked about last chapter would be a metallic situation. So do we have a metal which is held together by strong forces that we're trying to dissolve? Or is it something with hydrogen bonding or another polar substance which has dipole-dipole attractions? Or finally, is the solute that we're looking at actually held together by very weak forces like London forces? So these are another set of types of forces you have to look at here. And remember, over here, ionic and metallic, both of these are relatively strong. Hydrogen bonding and dipole-dipole attractions, a little bit weaker typically, but still relatively strong forces. And then finally, our London forces are typically nonpolar molecules, very weak forces, unless we get very, very large, very polarizable substances. And then the London forces can become very, very significant. So we have to break our solvents apart. We have to break our solute apart. And then finally, we form a new attraction. Bond formation is really involving a release in energy. So in this particular situation, we have a number of different things that can happen depending on what our solute and what our solvent are. Now on the top, the relatively strong attractions here, if we have something like sodium chloride dissolving, the sodium ions form an ion, water molecule forms a very strong dipole. This is going to be a fairly strong attraction. We're talking about ion dipole. If we have two substances involved with hydrogen bonding, once again, another relatively strong attraction. And then finally, a little bit weaker than the other two, but still what would classify as relatively strong, is if we had two polar substances. Those two polar substances are both going to have dipoles, so we get a dipole-dipole attraction. So the top three are really our stronger type of forces. The bottom are all of our weak situations. If we have an ion and a nonpolar substance, that ion can induce a dipole in our nonpolar substance. And we've talked about this idea before. Well, if we have a polar substance, it can also induce a dipole. And then finally, nonpolar substances next to nonpolar substances can induce dipoles in each other. Now, typically of these three, which are all classified as weak, this would be a little bit stronger, this would be a little bit weaker, and this would be the weakest of all. Unless we end up with something, once again, like very large molecules, and that would then increase the dispersion forces and increase the polarizability and the polar nature of that attraction. So making a solute to solvent force can involve relatively strong or relatively weak situations depending on what we've got it with. Now if you take a look a little bit closer at what's happening when sodium chloride dissolves in water. Now NaCl is soluble in water, and that's because the ion dipole attraction is strong enough to overcome the lattice energy of the salt. Now the other substance that we have to break apart is the water molecules themselves, but the lattice energy of NaCl is significantly stronger than that. So what really happens here is the attraction between the ion and the dipole in water must be strong enough to really overcome the attractions of the water molecules to each other and the ions to each other. Now if you take a look at another situation here, sodium chloride with C6H14. Now if you remember our organic chemistry, C6H14, that's going to be hexane. Now hexane, a bunch of carbons and hydrogens, is a nonpolar substance with relatively weak dispersion forces. Well, our solute in this case, sodium chloride, is going to have relatively strong forces. And what we end up with is the induced dipole situation, which is a relatively weak situation. My guess is that this would end up being insoluble, and that's because the solute to solvent attraction is really too weak compared to what we had over here to overcome the ionic bonding and make dissolving occur. Now the energy changes and solution formation is really looking at the rest of the picture. All we've really done here is talked about the intermolecular force component, but there was another component when we looked at the two things that can involve solvation. So when we're looking at this at a big picture, what we've just talked about, you really have three different processes that affects the energy of dissolving involving intermolecular forces. First would be the separation of the solute particles. They're together over here they're spread farther apart. That takes energy to break them apart. Well, if it requires energy, that's an endothermic process. The second situation would be the same thing from our solvent point of view. Our solvent particles are relatively close together here. Over here they're a little bit farther apart. That also requires energy. That's endothermic. The new interactions, now we're talking about making bonds. These two things over here come together and form new attractions in this situation. Well, bond formation is lowering potential energy. That's going to be an exothermic situation. So really when we look at the three processes involved, we have a couple of endothermic processes, and then we have an exothermic process at the end. The energy change overall of the process is really going to depend on the individual delta H's. So this would be what's happening when we are breaking apart our solvent particles. Actually, this would be the separation of the solute particles. This would be the separation of the solvent particles. Both of those are endothermic. They take energy. In this particular case, this releases a ton of energy when we form the solution, and overall this thing is exothermic. Well, remember we said if 3 was a strong enough situation or comparable to 1 and 2, we end up with dissolving occurring. So this particular type of situation, you would predict it to be, for an exothermic, you predict it to pretty much always be a process that happens spontaneously. So the dissolving would occur. But things really don't always occur spontaneously. Remember, spontaneous is, does it naturally happen or does it have to occur with outside intervention? Unless there is really an overall lowering of potential energy of the system, so overall exothermic. So one of the things we looked at basically last year in pre-AP with the idea of spontaneity was things that were exothermic tended to occur spontaneously, and when we ended up with an energy advantage through an increase in entropy, which we're going to end up looking at in a second, those two things are going to lead to an overall lowering of the system. Those two things are always going to be spontaneous. Well, in the case of what we're looking at here, 2 were endothermic, but the third was big enough exothermic to offset those two, and therefore that reaction would be likely to occur spontaneously. Now, we also know that you can overall have an endothermic reaction, like in this case, and some of these processes are water soluble and some of these aren't water soluble. So there have to be other processes at work here. So if we look at something like ammonium nitrate, this component separating the solute plus this component separating the solvent are larger than the energy we're getting back here. So overall this is an endothermic process. So in this particular case, energy has to go into the system. Well, I know when you put ammonium nitrate in water, it does end up dissolving. So there has to be something that offsets this difference in energy here. Otherwise, things like chemical cold packs, if you get injured, you break the inner seal, it gets really cold. That's basically ammonium nitrate dissolving in water. You know that's a spontaneous reaction. So in this particular case, it's endothermic. There must be something else at work that basically explains what's happening here. And the second factor is really the natural tendency of a substance to spread into larger volumes when not restrained. And this actually leads to lower energy when that occurs. So this is basically decreasing potential energy, which is more likely to make it spontaneous. So dissolving when it occurs is always going to be a spontaneous process. If I dump a solid in water and it dissolves, that's going to be a spontaneous situation. So if you remember from chemistry, reactions that increase in entropy, that means more disordered, more random, they tend to be spontaneous. Exothermic things tended to be spontaneous. The two together, always spontaneous. When the reaction was endothermic, if the increase in entropy gave us a great enough energy advantage, that would make the overall reaction still spontaneous, even though it was endothermic. And that's really the other component we're going to look at here. So really what's happening when we're looking at an increase in disorder, which is known as entropy, that's lowering the energy of the system, and that's an energy advantage. Now diffusion is always a spreading out of particles. They're becoming more random. So diffusion is a spontaneous reaction because of this very idea. It's when diffusion occurs, it's lowering the overall potential energy of the system, and that makes the reaction spontaneous. So even though enthalpy may increase endothermic, if the overall energy of the system is still a decrease because of increasing entropy, and the system is becoming more disordered, and that's a great enough energy advantage, then you're still going to end up with a spontaneous reaction and dissolving will occur. An example of this idea, silver chloride is essentially insoluble in water. So you end up with silver chloride, which is held together by strong ionic forces. It's an ionic substance. Now, you're breaking apart water molecule, which is relatively strong hydrogen bonding situation, while the dipole ion interaction is a relatively strong interaction. So this type of reaction could occur on the surface. But remember, silver chloride is insoluble. So that means you're not going to get that big energy advantage because of an increase in entropy. And we really wouldn't expect a significant change in the entropy of the system then when you put 10 grams of silver chloride in 100 grams of water. Since it's insoluble, you're not increasing an entropy of the silver chloride, and therefore you would predict it not to be water soluble. Now, one common misconception we're dealing with things mixing together. You need to understand, just because a substance disappears when it comes into contact with another substance, a solvent, that doesn't necessarily mean the substance dissolved. And that's really a common misconception. You have to look at the situation to understand when they came together, did you actually have a dissolution, a physical change where one substance was mixing into the other? Or did you actually have a chemical reaction? So if you can't get back the original solute by evaporating away, in other words, you can't physically separate it, it wasn't a physical change. So if it is a chemical reaction, you can't get it back, and therefore you had a reaction rather than a dissolving process. So you have to be careful when you're looking at a certain situation. Some things look like they're dissolving, but what they may actually be doing is chemical reacting. And the real idea here is keeping in mind that dissolution is a physical change. And if it's a physical change, you can physically get it back by reversing the situation. Section 3.2 gets into different types of solutions. And these are ideas that we talked about last year. First would be saturated. In a saturated solution, the solvent holds as much solute as is possible at a given temperature. So whenever you can't dissolve more solute at that temperature, then you have a saturated situation. And what's happening here is, if you're at the saturation point, your solid and your liquid are actually in equilibrium with each other. The rate of dissolving, this going into solution, is actually equaling the rate of recrystallization. So remember, equilibrium was when you have equal but opposite rates. Well, when you have a saturated solution with extra salt sitting on the bottom, it's actually still dissolving and it's still recrystallizing. It's just the rates of those two things are equal to each other, and therefore you have an equilibrium situation. Second situation we're going to look at here is an unsaturated situation. In an unsaturated solution, less solute, you actually have less solute dissolved than the solvent will hold. In this case, when you look at the picture here, at this given temperature of water, yes, you have some hydration occurring where you have ions dissolved, but notice there's a whole bunch of water molecules left here that could involve solvation of other things. So on a particle level, an unsaturated solution would have free solvent available to do more dissolving. Now, the last situation is the supersaturated situation, and this is not a common or normal situation. In fact, it's an unstable type situation, because what you really have is the solvent holding more solute than it really should at a given temperature. Now, these solutions, like I said, are very unstable. So in the top situation, this would be an example of a supersaturated solution here. When you just look at it, you can't tell that there's too much dissolved. But if we drop in a tiny little seed crystal, that gives us a site of recrystallization, and very rapidly we start to see all of these particles, which weren't supposed to be dissolved, coming out of solution. So Supersaturated solutions are a very, very unstable situation. Really, the only way to make it is increase the temperature. You can dissolve a larger quantity and then slowly cool it off. Some substances will stay dissolved even though they're not supposed to at that temperature until you initiate the reaction. Sometimes just shaking or jarring the reaction can actually cause the rapid recrystallization. Now, section 13.3 gets into factors that affect solubility of different types of solution situations. Now, chemists use this old adage or axiom known as like dissolves like, which really means polar substances tend to dissolve polar substances, and non-polar solvents tend to dissolve non-polar substances. That's the like dissolves like. Similar polarities are soluble. And what this really means is if there's a reason for interaction, they're more likely to interact with each other and dissolve. So like dissolves like is really looking at polarities of different substances. The more similar the intermolecular attractions are, the more likely one substance is to dissolve in another. So both of these substances have hydrogen bonding. You can see the hydrogen bonding here. There's hydrogen bonding there. They're likely to interact because of that hydrogen bonding. So if we introduce water into the situation, which also has hydrogen bonding, you would expect with two substances that involve hydrogen bonding, with water that involves hydrogen bonding, that you would get attractions between the two, and the two would likely be soluble in each other. In fact, this type of situation, they're so similar to each other, they're probably what we're going to call miscible. They can actually dissolve in any proportion. Glucose, which has hydrogen bonding all over it, you can see on this glucose molecule here, there's OHs in many different spots on this six-sided hexane or cyclohexane. You can see that there are lots of spots for hydrogen bonding to occur. When you have cyclohexane, there's no hydrogen bonding. So this is truly a carbon and hydrogen non-polar substance. So between the two, you would expect glucose to be very soluble in water, but cyclohexane to not be soluble in water. What fundamentally happens is the water molecules are going to attract each other, and they're not attracted to the cyclohexane, so those are going to separate out into a different layer. So what would happen to the solubility of glucose if the hydroxyl groups, remember the OH groups, the alcohol groups, were to be replaced with methyl groups? Well, as I get rid of these OHs, I'm basically losing my ability to be attracted to water. So as a nonpolar substance, the methyl group CH3 is going to decrease my solubility if I replace the OH groups with methyl groups. Another example, a lot of people take vitamins. There's different types of vitamins. Vitamins fall into one of two classes, water-soluble and fat-soluble vitamins. Vitamin A, which looks like this down here, is actually a nonpolar compound. Like a fat is a nonpolar compound, like oils are nonpolar compound. And that's because they're mainly carbon and hydrogen with just one little OH here on the end. So its ability to attract water is relatively small. Most of this substance is really a nonpolar substance. Whereas something like vitamin C, you can see on the vitamin C there's OH groups all over that molecule, which is going to make vitamin C significantly more soluble in water. Well, that's going to mean that these two things interact differently in the body. If you take extra vitamin C as a water-soluble substance, it's just going to be carried in the bloodstream and it get excreted out in your urine. Whereas if you take large doses of vitamin A as a fat-soluble substance, it's going to dissolve into the fat, and you can actually increase the concentration of the vitamin A so much inside the fats inside your body that it becomes toxic. So you never want to megadose something that is non-polar as a vitamin because your body is going to store that. Polar substances that are water-soluble, they get filtered out by the kidneys and dumped out of the body much more readily. Now, another thing that has the potential to affect solubility would be pressures. Now, before we really get into the pressure solubility, there's one thing I want you to understand that can happen if we have a gas in water. Now, as a nonpolar substances, gas solubilities you would predict to be relatively low. But remember, not all gases, not all nonpolar substances are equal to each other. As we increase the mass of the nonpolar substance, remember the magic word here, that would increase the polarizability, and it starts going to become more polar. So larger gaseous molecules are going to have stronger London dispersion forces because of greater polarizability, and that's going to make them attract water molecules better and therefore increase their solubility. So gas solubility is typically low, but intermolecular forces can play a role here into how much can actually dissolve. Now, the solubility of liquids and solids really doesn't change all that much with pressure. But the solubility of a gas is heavily dependent upon the pressure above the liquid. In fact, it's directly proportional to its pressure. And that's actually known as Henry's law. Henry's law, as a direct proportionality, if S is the solubility of the gas and P would be the pressure of the gas, Henry's law basically says it's S equals K times B. If you remember from our previous chapter when we got into the idea of graphically what that means, as P gets bigger, then S gets bigger. That's a direct proportionality. And a direct proportionality would look something like this. So one thing you might do is, if you know what the proportionality constant is for a gas in a given solvent, and you know the pressure, you can actually calculate what the solubility is. If you change the pressure, you can calculate the change in solubility using this equation. But one thing we did with all of these equations back in chapter 10 when we had all these direct and inverse proportionalities, another way to express this is to look at it from this point of view. If S equals K times P, then S1 over P1 is going to equal S2 over P2. If they both equal K, then they both equal each other. And this is really another way to use Henry's law. If we know the solubility at the beginning at this pressure, and we know what the new pressure is, we can use Henry's law in this form to calculate what the new solubility is. So there's a couple of different ways we can do Henry's law problems. So here's an example. Calculate the concentration of CO2 in a soft drink that is bottled with a partial pressure of CO2 at 4.0 atmospheres over the liquid at 25 degrees Celsius if the solubility at 1 atmosphere is 0.030 molar. Now, in this particular situation, they're giving us a solubility at a certain pressure, and they're giving us a new pressure situation. We can calculate what the new solubility would be. So in this particular equation, solve for X, and even though at 1 atmosphere normal pressure we can only have this much CO2 dissolved, when we pressurize the bottle with carbon dioxide, we can get a significantly greater concentration of carbon dioxide. But remember, when we open our bottle and we drop to room pressure again, 1 atm, all of that extra dissolved gas is going to start to bubble out as soon as we open the bottle of pop. Temperature can also have an effect on solubility. Now, generally, the rule is solid solutes in a liquid solvent increase with increasing temperature. So you can see, in general, most of these are going up as temperature goes up. Now, this is a general trend. So notice the word there, generally. If you look at the substance down here, that actually goes against the general trend. And this really depends upon the situation earlier we were looking at in terms of the strengths of the different types of attractions and what's actually happening with entropy in the reaction as to what energy or what temperature changes are going to do. But as a general rule, the hotter you get it, the more solid you can dissolve. So, general question here about cooking. Why do bubbles form on the inside wall of a cooking pot when water is heated on the stove, even though the temperature is well below the boiling point? Dump some water into a pan, sit it on the stove, and turn on the heat. And within a very, very short period of time, you will start to see bubbles form on the sides of the pan. Now, that's not gaseous water escaping because it's boiling. We're well below the boiling point. So think about the concepts we've been looking at to try and understand what's happening in this particular situation. Now remember, increasing the temperature of the water is going to decrease the solubility, and inside the water we have dissolved gases. Now we don't have a ton because gas solubility is relatively low in a polar substance like water, but it is there. And as you increase the temperature and your solubility drops, the released gases are really going to deposit on the sides of the container. So something simple is why when you put water on the stove do you see bubbles all the side well below its boiling point? It's really dealing with the gas solubility versus temperature idea. So for gases, the opposite is true as it is with solids. The hotter you get it, the lower the solubility is going to be. So carbonated soft drinks are going to be more bubbly when they're stored in the refrigerator because in a cold environment, when you open it and its solubility drops through Henry's law, it's going to escape more slowly if its solubility is higher because it's colder. So one of the ways to keep your pop from going flat is to try and keep it colder longer. That's really why we put pop on ice. We all think we like the taste when it's cold, but really the reason we started doing it was to try and keep it carbonated for a longer period of time, and now we're just used to that taste. Another effect can be what happens really with temperature in lakes and the dissolved oxygen amount. Now, oxygen is a gas, a nonpolar substance, not very soluble in water, but it is soluble to a degree in water, and fish actually use that to survive. They filter out in their gills the dissolved oxygen and use that to breathe underneath the surface of the water. While as the temperature of a pond increases, the solubility starts to decrease. And at your extremes, even though you're well below the boiling point, your fish are literally going to suffocate. And the ones that suffer first are the active hunting fish that really need the most oxygen. Those high metabolism fish that get their food from hunting other fish, those things are going to die first inside a pond. Whereas something like your carp and catfish, your slower bottom feeding low metabolism type of fish, they can actually survive in lakes that are at a little bit higher temperature. So if you ask somebody what kind of fish they catch in a lake, it gives you a rough idea about what is the highest temperature through the course of a season that that lake gets. If it gets too warm, it's not going to have many of your active hunting fish. And that basically finishes off our first set of notes from Chapter 13.